Howdy everyone, Mr. Kazi here with another lesson, and today we're going to do something a little different. I'm going to do some physics instead of chemistry, and I'm going to talk specifically about motion graphs. So get your graph paper out, get a straight edge and a pencil, and let's get started. In this lesson you will learn how to create a graph, distance versus time graphs, velocity versus time graphs, and the position equation. So let's get started. A good graph has a title, the x-axis labeled, the y-axis labeled, it has the proper units, and it is big. Size matters when it comes to a graph. I believe that if you have a little graph, then you have a little grade. You need to make a nice big graph. It needs to be readable, and it should be neat and clean. So let's look at how to prepare a graph. Draw your x and y axes, and then label the axes with your title, your independent and your dependent, and your units. And always remember, the independent goes on the x-axis. Mark off the units, make them nice and neat, and be sure to spread them out and count in such a way that you have a nice big graph. Alright, and then label your units. Graphs should be nice, they should be clean, they should be on graph paper. So be sure to take the extra time to make the graph look good. Alright. So let's talk about distance versus time graphs. Let's draw our axes. I'm going to label it distance versus time. Time is my independent in this case, and distance is my dependent. And how far I go, well, it's going to depend on my time. All right, let's draw a graph. There's our units, and let's label them off. All right. And there's my graph. Nice, neat, clean, ready to go. Let's interpret this graph now. Let's look at it here. There's the change in displacement. And there's the change in time. And if you recognize this, we are working with the change in displacement over the change in time. And that's just slope. And so if you look over here to the left, you'll notice that displacement over time is average velocity. And that's something we already know. And it's just the slope of a distance versus time graph. Slope is the velocity. And since velocity is constant, and you notice it's constant because it's nice and straight, and that means there's no acceleration. If velocity is constant, there is no acceleration, because acceleration is the change in velocity. All right, let's look at a velocity versus time graph now. In velocity versus time, we're going to label it up here. All right, let's put it together. Let's do that a little faster. And let's speed that up too. There we go. Now, in this case, we're going to look at our change in velocity and our change in time. That again is our slope, and therefore the change in velocity over the change in time is acceleration. That's right. In a velocity versus time graph, the slope is the acceleration. All right. Let's look at a couple points here. If we take 220 and 770, which I think you'll notice are the points right here and here, and if we work that slope out, and notice our units, let's just work that through. We get 10 meters per second squared, an acceleration. So the graph holds up, and so does the calculations. Now let's look at a distance versus time with acceleration. When we have a distance versus time with acceleration, and let's hurry this graph up. There we go. And there's the distance versus time graph that we saw earlier, but now we have an acceleration. And an acceleration means changing velocity. And so since we have a changing velocity, we are going to have a changing slope. Well, a changing slope is going to cause things to curve a little bit. And you'll notice there, look at that. That slope changes. And so we need calculus to work with this. And it's probably exactly why Sir Isaac Newton came up with calculus, and to help him work with curves. And since I'm sticking with algebra, we're not going to look at this that much. But I do want you to be aware of the distance versus time with an acceleration. When we have that, it causes just a little bit of a curve. You notice, basically, that was a parabola. All right. Now, what we want to do is look at how the displacement equation is derived from. We're going to look at a graphical explanation of the algebra involved in the displacement equation, which gives us our position equations. Let's look here. First, we'll label everything off. There we go. Did a little quicker this time. And there's our graph. Now you'll notice that we have an initial velocity at 30 meters per second. And then we have a uniform or constant acceleration as we go from 0 to 9 seconds. One of the first things we're going to learn here is that the area under the curve is the displacement, which I think is really cool. Which means then if I take off an interval, let's say the interval of 2 to 5 seconds, the area underneath there is equal to the displacement, which can be very useful. And using a little algebra, we can look and see that, well, that's a triangle plus a rectangle. And added together, that gives us the whole area. So we could look at their equations. The area of a triangle is 1/2 the base times the height. And the area of length times width is a rectangle. And we can add those two together, and voila, we have the calculations for the displacement underneath that graph. But that's in algebraic terms or math terms. Let's make it look a little bit better for us in physics based on velocity, acceleration, and time. I'm going to rewrite it, and let's let the base equal time. And you'll notice over here, that's exactly, there's the base is time. And so h is velocity, right there. And length is velocity. And width is time. Wow. So if I take my values here and substitute them into my equation, I get this new equation. S equals 1/2 the velocity times time plus velocity times time. But let's get a little acceleration in there. I know that velocity equals acceleration times time. And if I substitute that in there for velocity, then that's going to give me 1/2 the area time squared plus velocity times time. And that's not just any velocity. By the way, that's initial velocity. And I think if you look at that, it's very familiar to some of the equations and things that we've been using before. And now let's take it to the position equation. So I'm going to rewrite it. And I'm going to substitute position, or the change in x, for the change in displacement. Basically, they're the same thing. They're equal. And the change in x equals the difference. Something you always want to remember, there's always a difference in a change, or a change is always a difference. That means we're going to subtract. And so we have the final minus the initial. We made a substitution. Let's add x sub 0 to both sides, and we get 1/2 the area times squared plus velocity, initial velocity times time plus the initial position. And we can take, and I like to rearrange that, so I'm going to rearrange the terms. And by rearranging the terms there, voila, we have us the position equation, at least for horizontal. Now I'd like to rewrite that in a different form for the vertical, because notice that the acceleration here is going to be a little different. The acceleration, and something goes up and comes down, of course, is gravity. So there we have it. In the recap, we looked at the velocity is the slope of displacement, and acceleration is the slope of the velocity, change in velocity, or a velocity versus time graph. And position equations, we have the horizontal and we have the vertical. All of these are going to be very useful when we begin to talk about projectile motion. If you have any questions, send an email to Mr. Causey at mrcausey.com, or just go and subscribe to my YouTube channel. Lots of good information there. Check out Mr. Causey's world.com, and everybody have a great day.